Welcome here at the occasion of the International Conference on High Energy Physics, ICHEP 2024. This conference is the largest conference in the particle physics field, and we are very privileged to be able to host the conference these days in summer. We are just in the middle of the conference. The conference started past Thursday and it will last till Wednesday. And many of people here are actually participants of the conference, but this event is meant as a semi-public event, as an event also for the Czech public and journalists, etc. Just since there are more panels within this conference, not to confuse everyone, there was already some confusion. So I think this is not the panel where the directors will present their best ideas, which accelerators to build, and the others will be killing them and shooting them down. This will happen tomorrow, and this is not for public. This is. So if someone from the participants mixed up these panels, so you are still free to leave and to take dinner in downtown Prague, yes. But if you are, of course, welcome to stay. So I'm very happy to be able to present our distinguished guests who came to Prague on the occasion of this conference. And I would start from the CERN Director General Fabiola Gianotti. Director of the Fermi National Accelerator Laboratory, Lia Merminga. Director General of the Japanese National Accelerator Laboratory, KEK, Shoji Asai. Deputy Director for High Energy Physics of the Brookhaven National Laboratory, Dmitry Denisov. Director of the Institute of High Energy Physics, Beijing, Yifang Wang. Director for Research and Computing of CERN, Joachim Nich. Director for International Relations of CERN, Charlotte Varakaule. And the Scientific Secretary of the European Particle Physics Strategy Update, Professor Karl Jakobs. These people are here. They have usually nothing to do on evening, so they just took our invitation, but there are other valuable guests which surely have different evenings than sitting here with us, but still they accepted our invitation. And so this is the Deputy Minister of Science, Research and Innovation, Pavel Doleček. Head of Research Infrastructure Unit of Ministry of Education, Youth and Sports, Marek Vyšinka. Rector of the Palacký University Olomouc, Martin Procházka. Vice Rector for Research of Charles University, Ladislav Krištoufek. And Deputy President of the Czech Academy of Sciences, Jan Řídký. I'm Zdeněk Doležal from the Charles University, Faculty of Mathematics and Physics, and will try to moderate this evening. So, at the beginning, I would like to ask our guests to present briefly their laboratories, their facilities, their activities. So I would start from CERN Director General, and I would like to ask for the slides.
Thank you very much. Thanks a lot, and a very pleasure and privilege to be here Tonight I have 5 minutes and 120 slides. No, I mean 12. They asked me to stick to 5 minutes. I will try to be very fast, and I would like to say that, but with this alignment I can see my slides, so I have to, to stand. Thank you. So I just want to emphasize that CERN is science and actually much more than that. And actually our
mic closer to your mouth.
Yeah, but if I can move slides, I can. Okay, thank you. So our mission is based on 4 pillars: research, technology, innovation, collaboration, and education and training. So CERN is, it will take hours to go through.
This direction.
Well, okay. Then we go. Okay, so CERN is the largest laboratory in the world for particle physics. Particle physics is the most fundamental of all sciences because it studies the smallest constituent of matter and the universe, and the laws of nature at the most fundamental level. And this aerial view shows the ring of the Large Hadron Collider, the white ring. The Large Hadron Collider is the most powerful accelerator ever. And is the current project at CERN. So at CERN we want to understand how the nature works at the most fundamental level, and we know today that the smallest constituents of matters are the quarks, which are the fundamental constituents of protons and neutrons, and the electrons. So work at the Large Hadron Collider at CERN allows us to probe matters at the level of the quark, so on physical scales of smaller than the billions of a meter. So the Large Hadron Collider can be considered, can be seen as a giant microscope to study matter at the level of the smallest constituent. And these studies of the very, very small allow us to study, to also understand the very, very big, so the structure and evolution of the universe. I don't have much time to explain why, but maybe I can just tell you that when we collide our beams of protons in the Large Hadron Collider, the energy that we produce corresponds to the temperature that the universe had 10 to the minus 12 seconds after the Big Bang, which 13.8 billion years ago gave origin to the universe. So we are able to study the very first instant of the universe, and these temperatures corresponds to something like 100,000 billion times the temperature in this room. So this is what we produce daily and at every moment in the Large Hadron Collider. So in order to do this, I don't know why the computing doesn't show the picture, but anyway, we need 3 main instruments. We need accelerator, detector, and computers, and we need to develop cutting-edge technologies in many fields, which are transferred to society at no cost. So the Large Hadron Collider itself is a 27-kilometer ring, 100-meter underground. 2 proton beams are accelerated in the 2 opposite directions up to the highest achievable energies, where the only limit comes from the available technology, the technology of superconducting magnets. And they collide at 4 points where 4 big experiments have been installed in 4 underground caverns. And in a couple of years after beginning of operation, in July 2012, Atlas and CMS announced the discovery of a new and very special particle, the Higgs boson, which is related to the mechanism that allowed matter to form in the early universe and thus us to exist. So the Higgs boson is really related to our own existence. And I would like to underline that scientists from the Czech Republic contributed in a very important way to the LHC experiments and computing and to the discovery of the Higgs boson. So the technologies that we develop find applications in many fields. The World Wide Web is the most famous spin-off of CERN because it was developed at CERN in 1989. But also accelerators and technologies developed at CERN are used in cancer treatment using proton and light ions. Instrumentation or electronics developed at CERN is used in medical imaging. We develop superconducting cables that allow us to transport thousands of ampere with no losses, so they are very important, for instance, for the clean air transportation. We have a collaboration with Airbus, and so on and so forth. So there are still many outstanding questions in particle physics. The discovery of the Higgs boson allowed us to understand at least one of them, but there are many, many others, including the fact that 95% of the universe is unknown to us, is the so-called dark universe. And so we are at the moment studying the next big project at CERN, and the European particle physics community has recommended that to perform a feasibility study for a future circular collider as the most promising project in terms of physics potential, and it will be a bigger ring, 90 kilometers compared to 27 kilometers of the Large Hadron Collider, and will have an immense physics potential. It will be the most extraordinary instrument to study the law of nature at the most fundamental level. All this is possible thanks to the CERN member states. CERN was founded in 1954, so this year we celebrate our 70th anniversary with originally 12 member states. Now we are at 23 member states, 11 associate member states, and so on and so forth. And it's a real global laboratory with a population of 17,000 people from all over the world. More than 110 nationalities are represented, and the Czech community represents about 250, 280 people. So if you look at the age distribution of the community of the 17,000 people, you see that the peak is at 27. So this population is very young, and at any given time, CERN is training 4,500 young people, including physicists, engineers, and technicians, and only typically 30% of them stay in particle physics. Most of them go to other walks of life, industry, and other activities, and so CERN continues to produce high talented workforce in STEM, science, technology, engineering, and mathematics. So the Czech Republic joined CERN in the early 90s and is now contributing to CERN through several institutions that are listed here. They contribute to all the experiments at CERN, not only the LHC, but also experiments in other aspects of our program, and also contribute to high-performance computing. And the Czech Republic industry has been a very strong partner also for the construction of the LHC detectors with very high technology industries like Vacuum Praga and others. And I stop here. Thank you.
Thank you. Thank you very much. So may I ask FEMILAB director to present their lab?
Thank you very much. Thank you, Fabiola, for this wonderful introduction to particle physics as well. So FEMILAB is the United States' premier particle physics and accelerator laboratory. We operate the largest accelerator complex in the US, second largest in the world after CERN, and we have about 2,100, oops, not yet. And we were established in 1967, and our mission remains the study of the mysteries of space, energy, time, also for the benefit of all. Our flagship program is the study of neutrinos. Why do we want to study neutrinos? Because neutrinos are they are elementary particles which are the second most abundant particles in the universe after the photons, and yet we know very little about them because they are very hard, they interact very weakly, so it is very hard to detect them. And we believe that by studying them, we could unlock mysteries of some profound questions we could help answer about the universe, including why the universe is made of matter rather than antimatter. In other words, why are we here at all? So we have a comprehensive program for the study of neutrinos, which includes a long baseline experiment to Minnesota called NOVA, which has Czech collaborators on it since 2011, includes a series of a short baseline experiments, 3 of them. The most recent one came online just a couple of weeks ago, and we are building the DUNE experiment. DUNE stands for the Deep Underground Neutrino Experiment, which is built to be the best-in-class neutrino experiment and the definitive neutrino oscillation experiment in the world. And we expect that we'll be able to answer questions in a comprehensive and self-consistent way for many decades to come. The DUNE experiment is actually an international endeavor. It was internationally conceived, constructed, and will be operated. And it is the first international experiment of the Department of Energy on US soil ever to be constructed. And so the Czech Republic is a collaborator on the DUNE experiment, and so is CERN and many other laboratories and institutions from around the world. About 35 countries contribute. And the DUNE experiment involves building facilities at Fermilab, creating the most intense beam of neutrinos at Fermilab with a state-of-the-art new accelerator, and then sending them under the mantle of the Earth, 1,300 kilometers away to South Dakota, where at 1 mile underground we've excavated huge caverns to install up to 4 massive detectors filled with liquid argon, which is the state-of-the-art neutrino detector technology. And initially we're building to install 2 of them in order to write the neutrino interactions and study the neutrinos. By the way, DUNE being the first DOE international project on US soil is also the first time CERN is contributing to scientific infrastructure outside Europe, which is remarkable, which goes to say that particle physics is indeed global. We also have other priorities, especially the study of the Higgs boson and the energy frontier, and we do that at the LHC at CERN, and we have a big program with the CMS, one of the 2 big detectors. We're also contributing to the construction of the high luminosity upgrade of the LHC, both the CMS detector and the accelerator, and we're very, very happy to collaborate and together to push the frontier of knowledge. We also have a program with muons, another elementary particle. We have a couple of experiments for the study of physics, of signatures of physics beyond the standard model, and small experiments to search and possibly detect dark matter, as Fabiola mentioned, one of the outstanding questions of our field. We have world-leading technologies in accelerators, in radio frequency technology for the acceleration, high field magnets, high power targetry, and beam physics. And based on our expertise in computing, accelerators, detectors, we are now expanding in some new, emerging, and for the United States, critical technologies. And we are acquiring increasingly more expertise there, including quantum information science and technology, microelectronics, artificial intelligence, and machine learning. So I would like to stop here. I would like to acknowledge gratefully the Czech contributions to all our programs, including the students who come. We have about 16 students and scientists participating, and I would like to stop here. Thank you.
Thank you. Thank you very much. Yes.
So actually speaking, I'm familiar at the CERN. I stay in the CERN the quarter centuries, but today I have to talk about the KK. I'm sorry. Don't worry. Okay, so the KK is a multi-beam lab. So we have diversity programs. So we have 3 directions. The first direction is the basic science, particle physics, and nuclear physics. So the Super KEK-B and also the JPAC programs, T2K programs for the neutrino, and also the hadron fold. This is the particle physics and nuclear physics. Second direction is material science and also the life science. So we have photon factories, and also the JPAC, muon, material life science facilities, so that we can use for the neutron and also muon for the basic science, not only the basic science, also the life science, also material science. And and the third direction is advanced accelerators. We developed the superconducting accelerator and also the nanobeam technology. Using these technology, for example, that we can make energy recovery LINAC. For the energy recovery LINAC becomes more important for futures, since the carbon footprint is very important in the futures. And also the medical application, we use not the proton, we use the neutron for the cancers. So we have various programs. So the KK has multi-beams. So the E plus minus collider and photon factories and slow positron. It is very useful for the study of the surface of the material. And also that we have high intensity proton beams, and using this high intensity proton machines, we can use for the muon, proton, neutron, kaon, and also strangeness. The strangeness matter physics is very important for the hadron physicist. Next page, I have to do myself. So the first thing is Super KEK-B. Super Checo is a joined Super KEK-B programs. So the Fabiola-san said, so the after the inflation, so Big Bang is very important. So the LHC started about a study about of the just after the Big Bang. But another problem is after the Big Bang, why only our universe, the material only that exists in our universe? This is a big problem. There are two possibilities. First possibility is a quark makes this asymmetry. The second possibility is a lepton make such asymmetry. The first is a quark. So the Super KEK-B, the studies for the CP vibration in the quark sectors. So this is a very unique programs. We can produce a 10 to 11 bottom quark, charm quark, and also taus. And Super KEK-B is a luminosity frontier machines. So 10 to 35. Will be not yet obtained, but 10 to 35 will be obtained soon due to the nanobeam technology and also the very strong, powerful LINACs. So the nanobeam became a standard for the next E plus minus collider. And the belt detectors is a very interesting detectors, and the Checo groups joined the belt detectors, and collaboration in the 28 countries and more than 1,000 people. So the very interesting programs. And also the second possibility is a CP vibration in neutrino. So maybe I think maybe this makes asymmetry. This is my opinions. But so in Japan, the T2K programs is. So the neutrino and also the anti-neutrino is produced in the JPACs. And this neutrino is emitted to the super Kamiokande now. And also in futures, hyper Kamiokande will be produced. This figure shows delta CP and the chi-squares. As you can see, the large CP vibration in the neutrino sector will be observed, I think maybe soon. Yeah. So in order to search CP vibrations, we can prepare for the near detector. This is also the international collaboration, and also the intermediate water Cherenkov detector will be produced soon. And hyper Kamiokande is now the construction, and the Checo joined the hyper Kamiokande programs. And you can find that this dome has already prepared. Now the digging in the cylindrical bodies. So we can start, and also the photomarch tube is ready, is mass construction now. So we can start 2027. This is also very important programs. The final one is the next programs. So FCC is also very interesting programs, but Japanese likes smaller. So the LHC is 27 kilometers. The linear collider is smaller than the 27 kilometers, just 20 kilometers, relatively small. So and the important things is linear collider is energy upgradabilities. Currently, we use the superconducting technology, but in future, we can use another technology so we can extend energies. This is the benefit of the linear collider. And Japan may be the most small lab in these ones. So we need more collaboration worldwide. So currently, we are more international collaboration. I think in future, global collaboration becomes more important. Global is a more big collaboration in the worldwide. So currently, we make global frameworks. For example, the CERN is a hub laboratories in Europe, and Japan is a MOU between the Korea and also the Australias. And the United States has make a framework in the Japan-US funding frameworks. So that these tight collaboration for the future, I think may be the crucials in the world. So I think please join also the Czechos for the IRC technology networks. Thank you very much.
Thank you. I would like to ask the BNL representative, Dmitry Denisov.
Thank you. So can you put my slides? Yes, thank you. So while other lab directors were talking, I realized that I'm representing the oldest lab. So we were founded in 1948 and celebrated 75 years a couple of years ago. So it's certainly quite a bit. So BNL is located about 100 kilometers from New York. So and that's a real picture of the lab. So as we were talking about facilities, so we're concentrating on nuclear physics, particle physics, and material sciences. And as you can see from this aerial picture, so that's what main of our facilities are presented here. One of them is relativistic heavy ion collider, about 4 kilometers length, unique collider of heavy ions and all the way to the protons. We also have light source where a lot of material sciences studies are done. And our budget is approximately $1 billion a year. So for all of the lab, for all those activities, we have about 3,000 employees and about 5,000 users who are coming all over the world. And I will talk about our Czech users a little bit later. So we got 5 particle physics Nobel Prizes, so it's amazing, and 3 of them were actually obtained on so-called alternative gradient synchrotrons machine, which was built in early 60s and ran very successfully, so for many years, and still running, providing beams for the relativistic heavy ion collider. So what is our particle physics? So it's amazing because we work with basically everyone who is sitting on this stage. So we work very closely with our CERN colleagues, and we're leading US Atlas efforts in US. So you can see some of the facilities which we have of the lab in order to, for example, assemble high luminosity LHC Atlas tracker. We're working very closely with Fermilab on Dune experiment, properties of neutrino at short baseline, and protodune, and Lia already summarized these experiments. We are working on Bell 2 experiment at KK, so where we're leading the efforts in US on participation in this experiment. We're also doing quite a lot of astrophysics studies, and I will mention one interesting. This is Lucy Night. We're actually building particle physics experiment to put on the far side of the moon. So why? Because it shields from all the backgrounds, electromagnetic backgrounds we are creating. So we're trying to put it on the other side of the moon to understand early stages of the universe. And of course, we have a lot of various technologies which we're developing in superconducting magnets, in detectors, and in accelerators. So let me concentrate on relativistic heavy ion collider because this is, of course, one of the main facilities at BNL. So again, you can see here the chain of accelerators, unique accelerators which create polarized, the spins of the particles are oriented in specific ways and collide them at the S-Phoenix and STAR experiment, going through a chain of accelerator. So it's a unique accelerator complex, and all the way from a few GeV interactions to half a TV provides such interaction. So thousands of scientists all over the world coming to us. What I would also say is that we are also using particle and nuclear physics for applied application. For example, we have so-called NASA Space Radiation Laboratory, where we have beam with the size of like a meter by a meter to irradiate various objects which are going into space, for example, electronics. It appears that, look, these particle physics developed machines are extremely good, so we have huge waiting list for experiments by those who are sending their equipment in space to use this facility. We also have Brookhaven linear isotope producer. We're using linear accelerator. We're producing large number of isotopes, very unique isotopes, which we then ship all over the country in order to perform medical research. And our next step is electron-ion collider. So we are building electron-ion collider. So this will be new collider located at BNL. So it will help us to study strong force, understand proton mass and spin, and of course understand structure of the nuclear, because electron beam will perform opportunity to scan all parts inside the protons and heavy nucleus. And let me say a few words about Czech groups at BNL. So they are very actively involved in RIG STAR experiment for many years. So many of your scientists are leading this part of this experiment, like collaboration boards and many other. So Czech Technical University in Prague is involved, as well as nuclear physics. Czech Academy of Sciences is very actively involved. And right now, so we are concentrating, these experiments are running, collecting data for one more year. We will shut down RIG next year. So after that, we will concentrate on construction of electron-ion collider. And you can see here that also Czech group, you can see Czech flag, involved very actively in design and construction of this detector, Czech Technical University Nuclear Physics Institute and Charles University. And we hope that more Czech groups will join this exciting facility. Thank you.
Thank you. Please go ahead.
So IHEP is probably least known research institutions among all of us, but we are the largest research center for basic science in China. So we have a total of 1,500 employees, about $500 million annual budget, and we have about 1,000 students per year, plus also temporary visitors and so on. We have, our mission is mostly particle physics, but we're also working on the astrophysics, on the material science based on the synchrotron radiation facilities, and also spallation neutron source. So our major science facilities are listed actually here. Right now, there are 2 satellites flying in the sky at this moment. It's called Inside Hard X-ray Modulate Telescope, HXMT. And another one is a gravitational wave EM counterpart, All Sky Monitor, GCAM. So in the future, we have a planning of another 2 satellites in the sky to be operational, to be launched in the future. Right now, our institute is situated almost in downtown Beijing. We have one electron positron collider running since 19th, so up to now it's almost 35 years of operation. This is also one of the few E+- colliders still running at this moment. In this collider, we have a Beijing electron positron, a Beijing spectrometer called BES3, which is actually working since 2009, and we have been running for almost 15 years with a publication of very close to 600 papers. Going to the north a little bit, we have a new light source under construction. This is actually one of the most brightest light source under construction or to be in operation. Construction mostly finished, and we plan to have the first light by end of this year, and hopefully by next year we have this whole machine operational. Going towards south, we have a spallation neutron source, and then not very far from there, we have a neutrino experiment called the Juno, which actually looks at neutrinos from two reactor complexes in the south, so that we can, using these react neutrinos energy spectrum, to determine the neutrino mass hierarchy, and also we try to study astrophysics using neutrinos. Going towards west, we have a cosmic ray observatory called LASSO, which is actually air shower kind of detectors with altitude of 4,300 meters. So this is almost at the shower maximum of cosmic rays from the sky. And going further west, we have the CMB polarization telescope under construction, which we hope that in the next 5 years or so, we can grow up to a big, large facility for the CMB measurement, in particular for the primordial gravitational waves. We have been collaborating with the Czech universities for quite some time. There's another experiment which has been ceased operation. It's called diabetic experiment, and we have Czech group working with us since 2004, I think. And now we have our collaborators from Czech as a main player in the Juno neutrino experiment. So we very much appreciated our collaboration with Czech scientists, and we hope that the collaboration can continue. Thank you.
Thank you very much to all speakers in this roundtable. One would ask, is there any way these projects are coordinated in some way, or is there any cooperation? Is it a competition, or can particle physicists reach some agreement? And the best person to comment on this question is Karel Jacobs, who is now the scientific secretary of the European Particle Physics Strategy Update. So there is some strategy, and there is an update of it. And Karel, please tell us how smooth it goes.
Yeah, thank you, Zdeněk. Yeah, as you heard, the tools which we are using for particle physics are big accelerators, and you cannot easily build them in every country in Europe or worldwide, so it needs some sort of coordination. So the European strategy, as Zdeněk was mentioning, is, I think, a cornerstone of the decision-making process in Europe for the large facilities for the future of our research field. It also takes into account the worldwide landscape in particle physics, as well as advancement in related fields, like, for example, astroparticle physics or nuclear physics. So this European strategy process was established in 2005 by the CERN Council. The CERN Council is the supreme authority, decision-making authority at CERN, and it has representation from all the member states. Also Czechia is represented in the CERN Council, of course, with the Czech delegate. And so this CERN Council established this strategy process. And of course, this is a process which needs updates, because if you do the future planning, it needs updates. And in March of this year, Council called for the third update of this strategy. And the goal of this new round, the third round, is to establish the next large future facility at CERN, accelerator-based facility, which comes after the Large Hadron Collider. So why do we do this update now? Why was it called? As you heard already in the talk by Fabiola, in the last update of the strategy, there was so-called a feasibility study launched for a future circular collider at CERN. And CERN has presented a midterm report of this study earlier this year, in February 2024. In addition, there is, I think, a clearer picture now of the international landscape. In the US, there was a similar strategy process ongoing, and it converged in December last year with a report of the famous committee P5. They recommended as well a Higgs factory as the next important collider. In addition, they look far more in the future, where they target a muon collider on US soil in the very far future. Then in China as well, there was a presentation of a technical design report for the construction of a circular electron-positron facility in December last year launched, and probably the approval process is also ongoing and maybe converging in 25 in China. And also, as you heard from Shoji Asai, there is the ILC discussion ongoing in Japan, and a technology network was formed there. I agree, Shoji, it needs some global organization, but it still needs a lead lab to take the initiative, I think. Yeah. Yeah. So there is a lot of input coming together in 25, and that's why I think CERN Council, rightly so, decided that this is the time is ripe now to have this strategy update. So how is this strategy update going on? As I mentioned in the beginning, we need to find a consensus in Europe and also maybe worldwide on the next projects. And this strategy process is set up in such a way that the community input is extremely important. So already this is going to be a first step, and also the Czech community, the Czech particle physics community, is expected to provide input. A very important date there is the 31st of March 25. Now, this is the first step in this process, where everybody can give input into the process. Of course, if there's national input from Czechoslovakia, from Czech Republic, and Slovak Republic as well. Yeah, you know, I was born when this was still one country. When I went to school, I had to learn Czechoslovakia. Okay, so national input and also by individuals is expected on 31st of March. Then there will be two more stages. There will be an open symposium, which will take place at the end of June 25. The location is not yet fixed, but the date is fixed. It's going to be the last week of June, where the full community is invited to come and to discuss. To discuss also the input which was submitted on 31st of March. And we also will offer the national communities to take this input, which is appearing on 31st of March, into account, and to give a second round of the input before this symposium. And then we have a so-called physics preparatory group, which will present the findings. We foresee here a working group structure on different physics topics, physics areas, and we'll summarize this in a so-called briefing book, which will then be the basis for the final conclusions, which will be drawn in a meeting, in a drafting session in December 2025. Yeah? And these final conclusions will then be handed over to the CERN Council. The CERN Council is the final decision-making body. We hope that this final summary will provide the basis for the Council to take a decision on the next project to be realized then at CERN following the LHC. So that's roughly the scale.
Thank you. Thank you very much, Karl. So We apparently have bright ideas. We have bold plans, which we heard from all our directors around. We hopefully reach a strategy, or we have a couple of strategies. We know how to reach a strategy. So now we need to get through our plans, through the funding, which is of course very essential thing. The times where physicists got money because they won the Cold War are really, really over. And from the Czechoslovakia time. And so now every science field has to defeat and defend their plans, and also the social benefits, not just the scientific benefits, but also the social benefits. The economists work on these aspects, and there are books. One of the book, Maximo Florio, Investing in Science, classifies the outcomes, the social outcomes, not the scientific outcomes, of these large infrastructures, research infrastructures, in a few categories. And I will briefly mention them. One is the supply of skilled graduates and researchers, then new scientific instrumentation and methodologies, new firms and their technological benefits, IT development, and cultural and social knowledge. I wonder how our infrastructures deal with these things, whether there are some examples they are particularly taking care about or not. So may I ask, for instance, Lia, about how FNAL feels about the supply of skilled graduates, researchers, and like human capital?
Thank you very much for this question. It's an excellent opportunity for me to speak about a few things I feel quite strongly about. First of all, how do research infrastructures attract the best and the brightest, the workforce that's going to work on research? The first, of course, an obvious element is by offering state-of-the-art research facilities. Modern state-of-the-art facilities such as accelerators, high-performance computing facilities, detectors, and so on, attract the best workforce out there in order to conduct the research and to advance the frontiers of knowledge. So, for example, we at Fermilab have several state-of-the-art facilities. Accelerators, we're building now the state-of-the-art PIP2 that's going to produce the most intense beam of neutrinos. We have detectors that use the latest technology. We have high-performance computing. We have neutrino research facilities, as I mentioned earlier, and experiments, tools, and equipment. And we have quantum science and technology facilities, where scientists and engineers come from all over the world, for that matter, for sure the US, to apply very new and innovative technologies. Second argument, the research infrastructure creates a collaborative environment and an ecosystem that attracts the best researchers. Third argument, it provides career opportunities for those individuals who want to go into these technology and scientific fields, and it provides opportunities for hands-on learning. Next, it provides the opportunity, especially for some young kids, to work with some world leaders in the field all around and to receive international recognition by doing this work. They go to CERN and they work with Fabiola and other really fantastic physicists, and they come to Fermilab and equally and so on, all around. And then, some more arguments. It provides opportunities, Arai? Yes, thank you. Thank you very much.
We collaborate, as you can see.
Yes, yes. Thank you, Fabiola. To partner with industry, because industrial partners collaborate with labs that have state-of-the-art facilities, and so for those individuals that aspire for careers beyond academia, this is an opportunity. And then, of course, continuous innovation, which makes for typically our labs incorporate the latest emerging technologies and makes an environment which is very exciting for the young people out there who want to join the field. And another argument is they play a role in the regional economic development. And we see that very much in the United States, and in particular in the state of Chicago, where just last week, the state of Illinois came to an agreement with the Department of Defense, where each contributes up to $140 million for research in quantum technologies. So that's an example. And finally, my final argument is, it provides prospects for long-term careers in our field. And here I'd like to just end with a personal story. I did my PhD thesis work at Fermilab from 1987 to 1989, when the Tevatron was being commissioned at the time as a collider, and the person who was at the helm of the commissioning was Helen Edwards, the designer and builder of the Tevatron, and an amazing physicist. And the director of the laboratory at that time was Leon Lederman, and in 1988, he got the Nobel Prize. So every evening, as I was coming back from dinner, going to my office to work, I would pass in front of the control room. Every evening, Helen was in the control room, overseeing the commissioning of the Tevatron. This left an indelible mark in my memory, and my love for national labs stems from those days. And I've never turned around from that. So that's what research infrastructures provide. Thank you.
Thank you very much. It is very interesting. And Joachim, would you tell us something about these scientific instruments and the technical progress achieved in the infrastructures?
Yeah, Zdeněk, thank you, with pleasure. So you learned about particle physics and the big laboratories, and that what we are interested in, unraveling the innermost secrets of the universe. But in order to do that, we have to develop technologies. 3 big areas: particle accelerators, particle detectors, and computing. And CERN-DG has introduced us to that. So there is a lot of applications that our developments for accelerators and detectors and methodology have found outside particle physics, outside science, in our normal life. Medical applications, detectors. You saw this beautiful picture of the Medipix detector that makes very sharp X-ray images. A development that was started for detectors at, for instance, the LHC and other detectors. Particle accelerators. Most of the particle accelerators which are being built these days in the world are not for science, are not for physics, they are, for instance, for medical treatment, cancer treatment, all based on developments that have been done at CERN, Fermilab, and the other laboratories. We have heard today here in one of the interesting talks, and there was a sentence that is still in my memory: silicon photomultipliers will be the future of nuclear medical detection. Silicon photomultipliers have been again developed at CERN and other laboratories in collaboration with many universities, and they are now being used in detectors in these laboratories to do physics. But it's not only detectors and accelerators, it's also methodology, and it's sometimes amazing. I just this morning I scanned through a talk from our knowledge transfer department, like 40 different collaborations that we have at CERN. They're really amazing. Vaccine production, for instance, is being improved in collaboration with medical companies, with pharmaceutical companies, using artificial intelligence methods applied also in Higgs search, for instance. We have a White Rabbit project. Now, you might have heard the White Rabbit project already is a Netflix movie that you can see. I'm talking about another White Rabbit, which is providing picoseconds timing across long distances. Again, developed at CERN in collaboration with many other laboratories. And surprisingly, I learned that the German stock exchange in Frankfurt is using that. Apparently, picosecond timing must have an enormous economic interest. Yeah, maybe we should have solved this. Another, also from Germany, an interesting example, which I would have never thought. There's a company in Berlin called Bundesdruckerei. What their job is to produce German passports, German identity cards, and by the way, they also print euro bills. And we have a collaboration with them on identity management and cryptographics in order to improve, say, at one day perhaps, the security of bills. Now, this is all about the past. What is the future? I think we are now just starting at CERN big collaborations again to prepare the next generation of particle detectors. That was an initiative also launched by the last update of the European strategy, which we now, over the last years, put on rails, and which will again, I think, provide a lot of new developments. Accelerator, likewise, high field magnets to be developed for the next generation of particle accelerators, and many other applications for science. Quantum sensors, again, we had a very interesting talk today. Quantum sensors, a lot of this is still, I would say, speculative. It's not yet clear, but I'm sure there will be, in a few years, in 5 or 10 years, a lot of applications coming out of this, kind of development. Now, to stop here, Zdeněk, you might remember when we were still 20 years younger or so, we started a detector R&D project, which was supported by the European Commission in Brussels. We got some money together with, I believe, 23 institutions in Europe. And some of the topics I just mentioned, silicon PMs, were part of this project, the development. Also Medipix, the TimePix development was launched by this project. And I'm very happy that you, as part of the Czech community, and this is, I think, is a good example of also your important contribution. And I'm very happy that some of these developments, which we started as a young man, you remember, 20 years ago, which are now being applied in detectors at CERN and elsewhere. And I think I stop here. Thank you.
Thank you. I have to say that, yes, you had the skill to bring it all together. You were the coordinator of the project, yes, so I was just a member, but so... Okay, thank you. How in Japan, do you have firms working with KK or with research institutes or other people creating startups, or how is this in Japan?
Yeah.
It's on. It's on.
Okay, so I think maybe our community is not only the accelerator and also the detector, but also computing is very important business in our. And as Fabiola-san showed, the web, so HTTM is produced at CERN about 30 years ago, and And also very important things is big data, data grid for the LHC. It's planned about 30 years ago. So the distributed big data and also the connected high-speed networks and also the distributed data. So such an interesting proposal is made by the 30 years ago. Currently, the distributed computing is very common, but this is planted about 30 years ago. I think maybe it's very amazing. And currently, I'm afraid GAFA became some more strong. So I think maybe we need more tight collaboration for the worldwide, for the accelerator people, our groups, our community more make more communities and developed, for example, how to currently is a data center for the power consumption of the power data center becomes very high. So in order to reduce such a power consumption, I think maybe that we have a much collaborate. Such topics can be prepared. These are very important for the younger generation to make such companies. And also the quantum. He said that the quantum becomes very important. So university, I was director of the ICHEP of the University of Tokyo. At that time, many students working with the quantum business, with IBM and also the Googles. And they, unfortunately, they go to the companies, don't stay in the university or make new companies. But I think maybe that we make a more tight collaboration for also the quantum business and boost up our community in the quantum business and also make some companies, small companies for the quantum becomes more important. I think maybe such effort is necessary in our futures. Thank you very much.
Thank you. Thank you. I believe these benefits were quite sort of expected. What about the cultural benefits? Is it something we can also claim, some contribution? Who else than Charlotte could answer this question?
Thank you very much.
Please,
I also have 55 slides and 3 seconds. Does anybody have the clicker? That's perfect. I'll just add a couple of points. Obviously, the beauty of speaking after such a distinguished panelist that all the intelligent things have already been said. So I will just compliment a little bit about the value, the socioeconomic impact that research infrastructures have through people. Fabiola already said that at any one point in time, about 4,500 young people are at different types of educational training programs at CERN. I just wanted to dig a little bit deeper into what that means. So you can see here a couple of the examples, 900 graduates. We have at any one point in time 3,000 PhD students working at the experiments at CERN. We also have programs for bachelor and early master students. So effectively the whole gamut, and all of these again, important not just technical skills, but also skills in how to collaborate and how to work together, which are very prized when they leave the field. As Fabiola already said, about 30% of them stay, and that means that 70% of them bring valuable skills to society. Important programs for us are actually focused on high school students and especially high school teachers. I just want to highlight this program. We've brought through the lab over the past 20 years about 15,000 high school students. They're incredible multipliers, not just with the experiments that they bring into the classroom, but also the enthusiasm that they transmit by having new methodologies and by having a network of other teachers that they can work with. We're very proud also that the Czech Republic has been a great beneficiary of this program. We think there's more potential, so we hope it can continue also to be supported going forward, because this is an important way of engaging the next generation and encouraging this socioeconomic impact to continue. We've brought together now a number of these programs through a new delivery vehicle, our new education and training center, the CERN Science Gateway, which is a new infrastructure that we just opened in October of last year, all funded by philanthropic donations outside of the CERN budget, that has hands-on experiments and exhibitions for all age groups, age 5 to 105 plus. We like, obviously, to be ambitious. And you can see that there are really three objectives of this. First of all, to share, of course, the wonder and the beauty of science and the discoveries, and also the people at CERN. And also the second one is really to encourage the next generation to explore and to get engaged in a career in science and technology development, in IT and other professions. And the third objective is really to build bridges to society, and this is where the cultural aspect also comes in, and it's also a way to increase and to help enhance the trust in science, which is so important at the moment where so many of the challenges that we face as a global community will depend on advances in science and also in technology development and in how we govern all that technology. Now, just a couple of examples of the types of programs that we have: science shows, hands-on labs. We have also complemented this with online components for the educational programs, because of course we're on one site straddling the border between France and Switzerland, but we want to make sure that we develop and share these opportunities as widely as possible, which is why many of the programs that we have an online component to them. And you can see, of course, we have many important visitors, including the President of France. He didn't get stuck in. We hope next time that he will get a little bit more hands-on. I think, Fabiola, you need to encourage him a little bit more. Not the good moment. We've had just under 300,000 visitors already since October, so we will be more than doubling the number of visitors we had on site before the Science Gateway. So we can really see that there's interest and there is a thirst for this type of outreach and this type of public engagement. Now, we want to share much further, and one of the opportunities that we have to engage with different audiences is through social media, and I really want to highlight also Daniela is here. She's the one who leads this. Thank you very much. So this is her work, and if there are any mistakes in how I presented, they're entirely mine. We are present on 7 social media platforms. We have just close to 5 million followers across them, and you can see that Daniela and her team are gaining followers all the time. But most importantly, there's a very high level of engagement with the social media content that we have. And this is very important because this is really what matters. It's not just the clicks and the likes, but it's the engagement rates that we get. And that also allows us to reach new audiences and to get them excited about science. Now, I wanted just to highlight in a little bit more detail the socio-economic impact of this. With a very concrete example of a study that was done. This was done in the UK, but these types of studies have been done in other member states as well. This was a study that was commissioned by UKRI in 2019-2020 that quantifies some of the socio-economic impact of this educational training and also the popular outreach and the cultural aspect of this. And amongst some of the findings, and you can find this online, is that researchers that have been engaged at CERN actually increase their wage potential by 12% over a 10-year period. And also importantly, and I think this comes back to how you engage and how you reach out to young people, is that it turns out that 95 of physics undergraduates in 8 UK universities were attracted to study science because of activities in particle physics. And I think this is really it shows really the power of fundamental research to ignite that spark in young people to go into STEM. So just a couple of concluding thoughts, just bringing some of this together, is that research infrastructures really provide very unique opportunities and a very unique environment for engaging teachers and students of all ages. It's important to nurture this with dedicated programs, but also with dedicated funding. Fundamental research is really a very unique source of inspiration to encourage young people to get into careers in science. It's really the big questions that get them excited. And research infrastructures are really incredible facilitators of bringing that forward. But also, research infrastructures can be bridges to society that can really help build a connection with science and to help enhance the trust in science, which I think is particularly important today. And I think that again also comes back to the cultural element. So I will stop there with that.
Thank you very much. So I have one rather brief question to our panelists, and then I would definitely like to ask people who have some comments or questions, both our VIPs and other guests. And the question is, what should governments, funding agencies, institutions do to benefit mostly from their participation in our huge infrastructures, etc.? Is there anything they can do, they should not do, etc.? I know that Lia has some comments on this, so if you can present, what do you think on this topic?
Yeah, thank you very much. So I wrote a few thoughts, and then I want to end with an example from personal experience. So overall, first of all, is the governments and funding agencies must have a true commitment to science and technology, to advancing science and technology in a country. And then, of course, it's important to secure stable funding, because especially projects in research are long-term, as we've been talking here, are large, and they require stability in resources in order to execute, and in order for governments to be credible partners to their collaborators, because as we said, a lot of the collaborations are international. To be credible partners means stable funding. Then they must support and advocate international partnerships and create pipelines for programs to attract the next generation to the whole ecosystem. Now, this morning in one of the introductory welcome talks, I heard a couple of things that really attracted my attention. One is connect Czechia to the world. I think this is very powerful. All the collaborations with Fermilab, with CERN, with KK, Brookhaven, and China, and so on, are very important. And so the more this is encouraged and promoted, the better it is, I think. And the other thought I heard is the role of Czech expatriates, because they serve to connect the country to the rest of the world, and they promote Czech science abroad in that role. So I think the government should embrace the expatriates and put them to work for the country. It's of course very important in all of this to develop communication strategies to educate the public about the importance of investing in large research infrastructure. Because you have to always, all governments and funding agencies, all of us, as you said earlier, we have to really defend and explain why the country must invest in research, fundamental research, rather than in medical, in climate, so many other competing priorities. So communication and educating the public and engaging them in the importance of science is important. So here I want to end with a personal example. And I'm going to use Italy as an example. I believe this country is doing a brilliant job in incorporating science and technology, by the way. It's not only about scientists, it's about engineers as well. Incorporating science and technology in every discussion. Last week, we had at Fermilab the Italian ambassador to the United States visit our laboratory. Because our name is Fermi and because she's very deeply aware of the rich collaborations with INFN and with other Italian institutions, she has a natural interest in learning about what we do. She met the hundreds of Italian scientists and engineers and at the lab, interacted with them, and so on. I have met the Italian Prime Minister at her residence in Washington, D.C. about a year ago when the Prime Minister came. So science is in every political, governmental conversation. Every year, at the Italian embassy, they organize panel meetings, such as this one, where we are invited, nuclear physics, all the collaborators of the Italian INFN institution in the US are invited in conversations about the importance of science in general and fundamental science in particular. And so this is just one example where I've seen it, where the government, and of course the Minister for Science and Technology has been multiple times, and we've met her, to the United States, written signed agreements with the Office of Science, Department of Energy, and so on. This is an example where I've seen science and technology be so embedded in the government, and as a result, we have hundreds of brilliant Italian scientists and engineers working at Fermilab and, of course, elsewhere in the world. So this was my contribution to this.
Thank you, thank you. I think we do not have that many Czechs living abroad as Italians are living abroad. But we can still use it. This is a very good idea. Thank you for this. Fabiola, you also had some thoughts about this.
Yeah, thank you. So Lia already said a few things. She said very clearly, and I support this, of course, that projects in our field have long lead times. So sustained contribution and sustained budget is very important. So the first discussion, for instance, of the Large Hadron Collider about the possibility of building this collider took place in the mid-80s. Operation started in 2009, 2010. And now the upgrade will start in 2029, and the collider will run until 2041. So we're talking about 50, 60 years. So long-term budget stability. Another important thing is the following, at least for CERN. The member states, like the Czech Republic, they contribute to the CERN budget according to their net national income. But it's also very important that the member states also support their community of science at home. In some member states, I'm not alluding to the Czech Republic, this is not the case, but in some member states, the countries contribute to the CERN budget, but they do not support the community at home in an adequate way. And so they cannot benefit in the best possible way of what CERN can offer. Another thing that you, and now I'm talking to the Czech Republic representative, CERN is the laboratory of all the member states. So it's your laboratory. It's not based in the Czech Republic, it's not based in Germany, it's not based in France or in Italy, it's based in Switzerland, but it's the laboratory of all the member states. So the member states should use it as much as they can because it's your laboratories, and it's very important to profit from the opportunity that CERN offers. Charlotte showed, for instance, educational opportunity, training opportunity, knowledge transfer, etc. It's very important that the government keeps a very strong link with the scientists, for instance, with the council delegates, with the scientific community, because the scientific community can transfer to the government the myriad of opportunities that CERN offers. So these are my thoughts on this particular topic.
Thank you very much. I think it's time to pass the mic to for instance, Pavel Dolecek from the ministry, if he wants to comment.
Yeah. Well, first of all, thank you very much for the invitation. Thank you very much for the splendid presentation and explaining how your facilities work. Concerning what should governments do, obviously, as Lia and Fabiola mentioned, the stable funding is always a topic. Should I stand up or should I sit? What's more convenient? I'm not. Okay. Yeah. I started talking, and then I realized it's not that comforting for you to not see me when I'm talking. Now, I have to say, I would say it's the topic about stable funding. It requires something on the side of the infrastructures and also on the government. I'm very glad that through all of your presentation, there was a big focus on the socio-economic impact. I can hardly imagine that you would present your facilities without this. I mean, the time when the scientific impact itself was enough is far gone. When discussing about the, let's say, state administration, to be frank, you need that. Other thing is the focus on the interdisciplinarity, especially with particle physics, because you're developing unique technologies and you need to be able to prove that the application is also towards medicine, biotechnology, laser physics, and others. So there's the second part. And the third part, obviously what we want to see is the collaboration, making critical mass, making clusters. So I'm glad to see that there's many memoranda, many common joint projects, because we are not able to fund everything everywhere. So we need the critical mass to be created. That's the part of the national laboratories or let's say research infrastructures as such, and you do that, and I'm very glad. On the side of the state administration, I wouldn't say it is that easy that you need to fund all of the science and it will somehow happen. For example, in Czech Republic, we have the system that we are funding our membership with the international organization as a CERN throughout our contribution, and also in kind throughout projects of so-called large research infrastructures. That's the case of the CERN, that's the case of Fermilab, that's the case of Brookhaven laboratories, and so on. So we found some ways and tools how to fund our collaboration. We do that. But it's quite hard, and there are many representatives of our Czech scientific community. There is an inner competition, obviously, for the funding. There's inner competition not just about the fields in science, I mean medicine, nuclear physics, and so on. There's also competition via the tools that we are funding those. So I think that what is important for us is to say that if we want to be part of something such a large extent, like the laboratories or the big projects, the next big thing, the boson factory, whatever it is, we need to focus and we need to be able to say that those funding are, let's say, critical investment, and it's somehow being different part from the overall budget on research. Otherwise, there would be a problem because there are great agencies, there is institutional funding of research organization, and it's a whole one big budget. And obviously, if something such expensive occurs, there's inner competition and it's extremely political hard to justify that. So what I would like that we do is to say that those, like say, critical investment to those large-scale experiments, research infrastructures, is a special part of the budget, not being part of the rest. I mean, it's quite important, and that's the debate that we can move forward something. So that's for us. That's for our national debate. So I wouldn't say, and obviously you can say that you need to support the scientists via, let's say, standard grant schemes because you need to develop the skills. You can say that, and you're right. I mean, the whole science is one ecosystem, from the PhD candidates towards the excellent scientists that are participating in Fermilab. Obviously, that's one life cycle. But if you're discussing the functioning of state budgeting within the national countries, you need to differentiate those, and you need to put focus on those in different way. So that's my contribution.
Thank you very much. So do we have some, I think I can open already the discussion of, so do we have any comment on this? Any opinion from, yeah?
Okay, so in my opening speech on behalf of the academy, I mentioned that our Institute of Physics and Institute of Nuclear Physics participate in many of those experiments mentioned here by the representatives. But there are another, Czechia is also part of MEDIPICS in the effort at CERN, and there are another two institutes which do not have anything common with high energy physics. It's Institute of Physics of Material and Institute of Applied and Theoretical Mechanics, and they are part of MEDIPICS, and they are keen to get hands on new time picks and they use it. That was, so MEDIPICS was mentioned, so that's one thing. The other thing is that part of my life was devoted to extreme light infrastructure in Czechia here, and our electronics which drives our lasers is based on white rabbit. So it's a fast electronics. So that's for what concerns more the academy. And then just more light remarks. I guess if CERN would get 1 cent for every click on World Wide Web, Fabiola would have no problems with financing FCC. Yeah, fortunately it's not like this. And then what the public doesn't realize now, because now is a year we commemorate 55th anniversary of landing on the moon. And I guess that there are deeds like finding Higgs, which is effort-wise, money-wise, and it's comparable. And building FCC will be something similar.
Thank you. So, does anyone want to react or bring up some other ideas?
Okay. So I'll go in front of you so you can see my face. My name is Rupert Leitner. I'm working in the particle physics since 40 years or so. And well, my biggest worry about the future of the field is that when we are going to build a new project like FCC, there will be a gap of 6 to 8 years between the stop of the High-Lumi LHC and the start of the FCC project. And part of the community will be lost, in my opinion, because I remember very well the same situation from ending of lab at 2000 and beginning of the LHC at 2010. So the gap was very similar, even longer. But by that time, we are very grateful in that time to Fermilab because we have been able to work within the D0 experiment. Part of our community, E+ E- physicists, also started the Bell project in KK, heavy ion community in Brookhaven, neutrino program, reactor neutrinos in China, the accelerator neutrinos in Fermilab. But these communities are quite small compared to the particle physicists. So my question to Fabiola or other people is: do you see any way how to shorten the gap between the end of the High-Lumi LHC and the start of the FCC? Because in my opinion, it's very important.
Yes. Money.
Yeah, I know, but money are important, but people are even maybe more important.
No, what I mean is that the gap of a few years, but first of all, you can't run 2 colliders at the same time. So you have to first finish high luminosity LHC and then start after a few years, I say. But that gap can be reduced to 2-3 years. But the reason for starting the next collider around 2045, 2048 is because we have to accumulate enough money, enough resources from the CERN budget once we have stopped running a collider, because 80% of the CERN budget is absorbed today by the operating costs. So running the site, running the scientific facility, and in particular the Large Hadron Collider, which then become high luminosity LHC. So today we have an investment capacity from the CERN budget while running the LHC of about 300 million Swiss francs a year, which we are using now to upgrade the LHC. The day we stop high luminosity LHC, the 300 million become 800 million. So you see in 3 years you accumulate 2.4 billion. And so those years give us the oxygen to complete the funding for the future collider, FCC or whatever. So I think it's important that to remind those numbers. And so we can start earlier, but it's a question of getting the resources. So if we can get contribution from United States, Japan, China, just send some messages. Then we may start earlier.
Thank you very much. Yes, please.
I think Rupert brought up very interesting opinions about this. I think the whole community should think about this carefully. I think in old days, we all have different projects in every continent or every country in the past. So he just made many examples. So I think in the future, it would be great that we have projects, smaller or larger, in every continent either. Otherwise, having only one place for high-energy physics is not good. That's exactly for this reason that we proposed the CPC, and we hope that we can inject additional 5 billion euros into the community. Otherwise, without CPC, I think money is not going to be there.
Thank you. I think we are coming to the end of the time block we have. So are there any further comments, questions?
Yes. Oh, I attended the university as a physics major at the turning of this century. And it was at that age that conducting super collider event happened. And the students around me has fly away from particle physics. So my question is, what has been learned from the previous project, and what can we do better this time?
So, I don't know who wants to take this.
Okay, let me try. And look, I'm trying because my ID number, I was SEC lab employee, so it was -1 from the last. So I actually arrived like a week before the Congress vote. So I have some personal connection to this topic. Look, I think that it, of course, was sort of not what we expected, but I think one of the important points which we all present here is that at that time, SSC was not as international as it would be nice sort of to have. So as a result, of course, it was very sort of concentrated in one country. And of course, there were, for various reasons, sort of reduction in funding for very large facilities, and of the Cold War we mentioned. So, and that certainly didn't help. Although the idea of the machine and implementation of this machine were great. I think one of the probably most important lessons for the community, and I think we are following it pretty closely, is to be strongly international.
And I want to agree very much with what Dimitri said. The direct lesson learned is applied to LBNF and YUN, which, as I said earlier, it is designed from day one as an internationally designed, constructed, and operated project, rather than international partners being an afterthought, like in the SSC. Partners help to design from the beginning.
If I may, I think I'm not going to comment on the SSC, but we have seen today, just from us, and we are not, there are other labs in particle physics in the world, how a rich program these labs offer. So, for the young people, they can work on colliders, they can work on neutrinos, they can work on fixed target. There is a richness in the field, which is quite amazing in terms of physics facilities, scientific facilities, in terms of technologies being developed, in terms of training opportunities in international environments. So these, I think, are quite unique opportunities for the young people. There are not so many fields where you have, the variety of facilities and scientific goals and objectives and training opportunities in international environment, technologies being developed as in particle physics. So I think it's still a very vibrant field. And the field that really offers the opportunity of working with people from all over the world, which is also one of the things that attracted me into particle physics.
So, Penny?
I just want to make a comment about the super collider because it was something that I was involved in also. And I want to say that you should not use what happened with the super collider as an example of what might happen here, because that was a very special case. As Dr. Weinberg said, it became a political football. And what he meant by that was the community had ample opportunity to keep it alive. For example, when Bill Clinton took over, it's true we were up by a factor 2 on the budget, and he did say, I need to show some restriction, show that I'm putting it under control. But he offered a quite reasonable opportunity. He said, oh, okay, I'll give you 21, half of the magnets for sure, and if my budget improves, which it did because he went out with a surplus and a booming economy, I'll give you the rest of the magnets. So we would have at least had 21 TeV in 1999 if they had accepted that. But the men, Professor Drell and the others, told me that they were going to tell him 42 or nothing. Now, it's a weird response to his. Obviously, he had a political problem because the budget was a problem and the economy was slow, so he had to do something. And the fact that they refused 21 TeV for sure, 1999, we still haven't reached 21 TeV in PP collisions, means that was a purely political decision. It was not about, using that as an example about what might happen here in Europe. We had internal disagreement at the leadership of our field about whether we should make the super collider. We had people with Nobel laureates, like Dr. Richter, who told me that if that machine is completed, my lab will be destroyed. He told me that. And when you have that kind of disagreement in a field, obviously the government is at some point not going to be able to go forward because they need agreement in the field. As long as you don't repeat that, I don't think you have to worry about what happened with the super collider.
Thank you. Thank you. I'm afraid we have to come to a close, so let me thank our guests for both for coming, but also for their long-standing support of our field. We know all of them. They visited CERN. They really support our field, and I'm happy there is this program of large infrastructures, which we discussed about the budget, but definitely not about it will stop or something like this. Now we have some new funding, and it can be well the administrative nightmare of the new programs compared to these large infrastructures. We are really jealous about the way. Sort of easy way how to spend money from infrastructure. So I'm very grateful to our VIPs and thank them for joining and for this support. And I'm really very happy that we could gather these distinguished people at our stage, and they shared their experience with us. And I wish them the conference to find some time for Prague, and not only just these discussions. Thank you very much.